This is the second lecture of Chapter 17, which deals with electrophilic aromatic substitution reactions. In this presentation, we will cover the following. First, we will do a quick review of aromaticity and aromatic compounds. And then we will go right into electrophilic aromatic substitution reactions. We'll also look at the mechanism that's involved because, of course, as you know, the mechanism is of extreme importance in understanding how reactions work and how to explain products that are formed. Next, we'll look at a very important reaction, nitration of benzene. Then we will concentrate on the halogenation of benzene, which is mostly bromination and chlorination. Then we'll concentrate on the alkylation of benzene. This reaction is also known as the Fieldcraft's alkylation of benzene. And lastly, we will apply electrophilic aromatic substitution to the synthesis of larger molecules. So let's begin. As a review, there are a lot of molecules, I should say, in nature are aromatic. So it's important to determine which molecules are aromatic or not. And we had some criteria that we listed in the last lecture. So we'll just quickly review them here. And one that's of importance here is that aromatic compounds are very stable. Benzene, for example, is an aromatic compound and it is used as a solvent, extremely stable. We'll see more later on in this chapter. Next, the structure must be cyclic and conjugated. The importance of double bonds. Remember, conjugation here means alternating bonds with single and double bonds. Equally important, must be cyclic, must be in a ring. Another very important criterion is that of Huckel's rule, also known as the 4n+2 rule. What this means is that you will have to determine the number of electrons in the system that you're analyzing and plug it into this equation. So 4n plus 2 equals the number of electrons that you have determined. So if it's 6, for example, you put 6 there and you solve for n. If n is an integer, such as 1, 0, 1, 2, 3, a counting number, the system has passed Huckel's requirement. If it's not an integer, such as 1.5 or 2.5, it fails Huckel's requirement for being aromatic, and hence the molecule is not aromatic. We also mentioned that each atom must have one unhybridized orbital. What happens here is that we need orbitals for electrons to resonate or be in resonance throughout the cyclic system. And of course here we mentioned that there is a continuous ring of electrons through the conjugated system. So once you know these criteria, you can look at just about any molecule or ion and determine if it's aromatic or not. I think I have some examples here. So here we go. Here's benzene. And the reason why I highlighted benzene here in a box is it is readily available. It is cheap. It comes from fossil fuel. So we have a lot of benzene available. And that's what will be used for our reactions. So it is aromatic because it's cyclic, it meets Huckel's rule, and as you can see here, this one here is not aromatic because it has 8 pi electrons, so it does not meet Huckel's rule. This is aromatic because it has 6, even though it has 2 electrons here, non-bonding electrons on nitrogen, but they are also a part of the ring of conjugation. Here is another one, 2 pi electrons here, so that meets Huckel's rule because here N is 0. This carbon here is sp2, but vacant because these bonding electrons here are mostly associated with the electronegative oxygen. This system here is aromatic because we have here 10 pi electrons. Again, note that these electrons here are not part of the aromaticity. They are orthogonal to the plane of these 10 electrons. And this is not aromatic because we have 2 4 pi electrons, and that does not pass Huckel's rule. Note again that even though this is sp2 with a vacant p orbital, it does not meet Huckel's rule. So again, you should be able to look at molecules and determine if it's aromatic or not. And the importance of doing so is that aromatic compounds are of extreme importance in organic chemistry. Let's concentrate now on the reactions. The name of the type reaction that we will cover, it's a substitution reaction, but it can be further defined as electrophilic. Electrophilic here, as you recall, means a positive species, electron loving. And aromatic, of course, aromatic is a part of it because we will be working with aromatic molecules. So the name of the reactions that aromatic system undergoes will be electrophilic aromatic substitution. So again, it's called a substitution reaction where a hydrogen on benzene, as I mentioned, benzene will be used a lot here because of it is readily available. So if we substitute one hydrogen for an electrophile on the aromatic system of benzene, we have an electrophilic aromatic substitution to produce here a substituted benzene. Just as a reminder, E plus is electrophile, electron-loving species, so it is positive or partially positive. So all the electrophiles that we have looked at throughout this course, we will consider them here as potential reactant for electrophilic aromatic substitution. Let's look at the mechanism. The mechanism here involves a pair of electrons. Notice here's a pair of electrons, 2 electrons, can in fact swing out or react with electrophile. So the electrophile here is positive. It needs electrons. The benzene ring here is nucleophilic. It has 6 electrons. So in the initial step, it gives these 2 electrons here to form this bond right here, to form an intermediate. Notice this intermediate here is not aromatic, whereas this is aromatic, very stable. So this step, as you can imagine, is slow, the rate determining step. In the last step, the proton is lost as H plus, and these electrons here swing back in to form the aromatic compound again. So that's fast, as you can imagine, because it forms a very stable product. So we have a rate determining step using 2 electrons to form an intermediate, and then a fast step to produce the substituted benzene as shown here. So let us start by looking at specific reactions. The first reaction that we look at is the nitration of benzene. As you can imagine, the name implies adding the nitro group to benzene. So here's the H, here is the substitution NO2. Here is a catalyst. The reactant here is HNO3 and H2SO4 is the catalyst. To fully understand how these work, let us look at the mechanism. So we need to generate here the NO2 plus, that is the electrophile. So sulfuric acid is mixed with nitric acid. Sulfuric acid is a much stronger acid than nitric acid. So sulfuric acid, being a stronger acid, will protonate nitric acid, as shown here. If it protonates right here, as we have seen here, you will recognize this to be a very good leaving group. So this leaves as water, and what's left behind is the nitronium ion, or the electrophile, which will then react with benzene. The next slide shows that mechanism. So a pair of electrons, as you can imagine here, reacts with the nitrogen, which is now the electrophilic atom of the nitronium ion, in the rate determining step to form this bond right here, which means that this carbon will be positive because these electrons swing out to form this bond. As you can see here, this is not as stable as the reactant because it's not aromatic, but it is fairly stable because this charge can be delocalized throughout the ring, as we have seen here using resonance. In the final step, a proton is lost, so this is lost to give H+, and these electrons swing back in to form nitrobenzene in a fast step. So this is the reaction of benzene with nitric acid and the catalyst sulfuric acid to produce nitrobenzene. Let's look at another reaction here, and this is the bromination of benzene, adding bromine. So these reactions, of course, as I mentioned, require an electrophile, because the benzene is a nucleophile. So what we need here is Br+. I know that looks very unusual because Br is an electronegative atom. It's to the extreme right of the periodic table, and it's extremely large. So you'd expect it to be Br dot or Br negative. But what we really need is Br+. So we'll have to generate it. So, and that's the catalyst. That's why we need a catalyst. So the overall reaction is benzene reacting with bromine, and very important, a catalyst will generate here bromobenzene and HBr. As you can imagine, H goes over here, and one of the bromine goes here for the inorganic product, and the other one goes as the organic product. But let us see, how do we make this Br+, the electrophile? The catalyst is FeBr3. It has a vacant orbital as illustrated here. Bromine has lots of electrons around it, as you know. So it's possible for these electrons to bond to this orbital or to interact with this orbital. If these electrons interact with this orbital, what's generated is this species where the electrons now flow towards the iron, making it partially negative, and this bromine here partially positive, electrophilic, as shown here. So this is an electrophilic bromine. So in this reaction, you really do not generate Br+, as a species existing by itself, but an electrophilic bromine that's bonded to the catalyst. So in the next step, as you can imagine, here are our two electrons, or any two from benzene, reacts with this electrophilic bromine. The electrons go over here to form FeBr4 negative and our resonance stabilized intermediate. Okay, that's the rate determining step. Why is it the rate determining step? Because this is aromatic and this is not. So therefore, this is a slow step. In a fast step, as you can imagine, this proton is lost to one of the bromine negatives here to get HBr, and of course we have generated our bromobenzene. So once again, for bromination, it's Br2 in the presence of FeBr3, the catalyst. So for these reactions, please do not forget your catalyst. I hope I've convinced you that the catalyst is needed because benzene is such a stable molecule. It needs a catalyst if it's going to react to form a product. As you can imagine, we can use chlorine. So chlorine in the presence of FeCl3 will produce here chlorobenzene. Iodobenzene is just so unreactive, and iodine is just so unreactive, and fluorine, as you can imagine, is just too reactive. So the halogen that's typically used for the halogenation of benzene is bromine or chlorine. Okay, let us look at an application of what we just studied here. So, is it possible for you to demonstrate how to convert benzene into benzoic acid, as shown here? As I mentioned earlier, benzene is readily available from fossil fuel mining, and so it's a good starting material. The challenge is that it's very stable, so we'll have to figure out what catalyst to use and how to convert it to another molecule. So let's do the analysis and retrosynthesis. So here's our target molecule. So we recognize that we have to make this bond, as shown here. Need to make this carbon-carbon bond. We recognize here this as the carboxylic acid group, which can come from CO2 reacting with a Grignard reagent. Once again, do not forget the chemistry that we have covered. We are building on the knowledge that we've gained so that we can become more versatile in our application of the chemistry. So this is a reaction that we have done. However, if the starting material is benzene, it has an H, so we'll have to convert that H to a halogen for this reaction to work to get our Grignard. So once you have figured out what's needed, it's just a matter of putting together the type reactions and reagents. So the type reactions that's needed here is a reduction of carbon dioxide using a Grignard. Of course, you can make a Grignard with a chlorobenzene, and you can make a chlorobenzene by an electrophilic aromatic substitution reaction. Notice I'm using here chlorine because chlorination is much cheaper than bromination, much more cost effective. So let's put the reagents in. So the reagents here would be Cl2 as the reagent, and most important or equally important is the catalyst to create chlorobenzene. We have magnesium here in the presence of ether, and this of course is the Grignard reagent, partially negative right here and partially positive here. So this is nucleophilic. It reacts with carbon dioxide, as you will recall. Here's carbon dioxide, here's partially positive. So these electrons here will react here to give that, and after protonation we have our carboxylic acid. So once again, folks, please do not forget the chemistry that we have done. We're constantly building on it and introducing new chemistry. Here's another example, one that we have done, I think was for the quiz or one of the tutorials. Starting with benzene again. So what you'll see here is that most of the reactions or synthesis that we will do, we will start with benzene because of it is readily available. Here's the target molecule. So let's do the analysis as shown here. Need to make this bond because we start with benzene. And of course we have here an amide, so we can make this bond again using diethylamine and reacting with an acid chloride. Why acid chloride? Because it's a carbonyl with a good leaving group, so the reaction here is an acyl substitution. And of course, as you can see here, this is carbon dioxide reacting with a Grignard, which you'd have to make, and converting to a good leaving group to add your diethylamine. Here again we have benzene, which has a hydrogen. We need to convert that to a halogen using an electrophilic aromatic substitution, and then we can convert it to a Grignard reagent. So the overall reaction is using bromine and FeBr3, we have bromobenzene, electrophilic aromatic substitution reaction right here, Grignard reagent, magnesium, ether as a solvent to produce our Grignard reagent. Grignard reagent is very reactive because this carbon here is nucleophilic, very negative, reacts with carbon dioxide to form carboxylic acid. Poor leaving group, as we mentioned from the last chapter, so we can convert that poor leaving group to a much better leaving group using thionyl chloride. Of course, that's just one reagent. Remember, there's another one called oxalyl chloride. Once you have converted it to a good leaving group, you can now react this molecule with diethylamine to get our target molecule. Notice here, I deliberately used bromine just to demonstrate to you that it's possible to make a halogenated benzene. But it's not the most cost effective. So it would have been more economical to use chlorine and FeCl3 here. But this is not a wrong answer or wrong response. Alright, let us turn our attention now to the alkylation of benzene. How do you convert H here into an alkyl group, a carbon containing group, which we have defined as R? What you'll need here is an alkyl chloride, and don't forget, you'll always need a catalyst whenever you are reacting benzene with another molecule. As you can imagine here, the electrophile will be a carbocation. So the electrophile is a carbocation to make that substitution. How do we get that carbocation? Here's an example. Here's chloromethane in the presence of a catalyst. This time it's AlCl3, a strong Lewis acid, which has here a vacant p orbital. A vacant orbital. As I've mentioned earlier, there are lots of electrons on chlorine, and it can bond or occupy this vacant orbital. If that happens, the electron will be pulled towards the aluminum, making it partially negative and making our CH3 here electrophilic, or more like a carbocation. Notice I'm saying more like a carbocation because, as we'll see in the next slide here, It's not really generated as a free carbocation because you know that a methyl carbocation is not stable. So it may not be generated as a free CH3 plus, but still bonded to the catalyst. But the bottom line is this carbon here of this methyl group is electrophilic. A pair of electrons can bond to it, and then the electrons shift to the aluminum, making AlCl4 and our intermediate. A rate determining step again, because this is aromatic, this is not, so it's a slow step. In a fast step, you can imagine here one of the Cl's minus from this product here abstracts this proton to get HCl, and the electrons move back in to form here our methyl benzene. So that's how you can convert benzene into methyl benzene. Of course, as you will recall, that's also known as toluene. That's another very popular solvent that's used in industry and in the organic chemistry lab. There's a problem, however, with the Friedel-Crafts acylation. By the way, this type reaction, the alkylation of benzene, is also known as the Friedel-Crafts alkylation, after the name of two chemists who discovered this reaction. There's a problem because there are unexpected products that are often observed. So if we have this reactant, alkyl chloride, we react it with benzene in the presence of a catalyst, yes, you will get the expected product, because here will be our partial positive. So here's that carbon. But here is an unexpected product. So if you're working in industry and you're asked to make one of these, it will be very difficult just to get one, because you get an unexpected product. As chemists, we need to understand where this unexpected product is coming from. And it's a large percentage. More than 50% will be the unexpected product. So to explain that, we need to look at the mechanism. So let's look at the mechanism. Here is our starting material, chloropropane. Here's our catalyst. As expected, we will form here this intermediate where the chlorine bonds to the catalyst, so we have a partial positive or a carbocation-like intermediate here. Notice this is not a methyl carbocation, but now it's more like a primary carbocation. So it may, in fact, and it will, leave the catalyst to form a primary carbocation. But here's a challenge. The less stable carbocation that's formed here, we can have here a hydride migration, where these electrons and the H moves over to here. So here it is, and what's left behind is a positive charge, which is now a secondary carbocation. You will recall that the stability of carbocations are tertiary, much greater than secondary, much greater than primary, and much, much greater than your methyl. So if we have a primary carbocation, as shown here, it will rearrange to give the secondary carbocation as shown here. So you know what's going to happen. The benzene will react with this one, and it will also react with this secondary carbocation. But we will get a lot of this reaction because it is more stable and you'll have more generated. So let's look at what happens. So here's our primary carbocation. the benzene, 2 electrons from the benzene, as expected, reacts here to form the resonance stabilized intermediate. And in the rate determining step, as expected, because of the stability of the benzene. And in a final step, the intermediate loses a proton to regenerate the aromaticity and the new product. So this is the expected product. Expected product. But let's look at this. The secondary carbocation, which is generated by a 1,2 hydride migration, as we have seen before, will react similarly. Benzene, 2 electrons from benzene reacts here. So here's that carbon. This carbon is right here. And of course the resonance stabilized intermediate in the rate determining step. And in the final step, this proton is lost, as shown here in a fast step, and the aromaticity is regained to give the unexpected product. This time is isopropyl benzene. So as you can imagine, the alkylation using an alkyl halide and a catalyst AlCl3 is not used a lot in synthesis because of possible rearrangements and possible unexpected products. But we'll find a workaround before too long. Let us look here at another type reaction, very similar, because we can generate here a carbocation. So let's look at this. This is an alkene in the presence of an acid. This mixture, the benzene, the alkene, and most important, the acid catalyst, acid as a catalyst. So we're not using aluminum trichloride here, we're just using HCl. But the bottom line is that this is an alkene. No, this is an acid, and we know from previous chemistry that there is an addition reaction that will take place because the alkene, which is nucleophilic, will react with the H plus of the acid because it is partially positive to generate a carbocation. Once you have a carbocation and you have benzene in the mixture, a reaction will occur. So let's look at the mechanism. So as stated, here's the alkene, and addition with the acid will generate a secondary carbocation right here. A problem though, this is a secondary carbocation, so it's possible to have a 1,2 hydride shift. Remember, hydride is H with its electrons, a pair of electrons and a negative charge. If this entire H with the electron migrates over to here, we have a positive charge right here, which is now a tertiary carbocation. So this is more stable. So once we have a carbocation, it will react with benzene, as we have seen before, to create the intermediate in the rate determining step, and of course not very stable, at least not as stable as the aromatic ring. So these electrons will come in, as shown here, to form the double bond. So we have 6 electrons again in the ring, and here is our unexpected product. So you got to look out for these type reactions. I think this is the end. Yes, it is. So once again, continue reading your text, continue to watch these videos. They are introducing some new type reactions, so take your time and watch these videos. I know at points you may have to pause and get your pen and paper and just write these things out just to make sure you understand it, and equally important, you can apply it. And so that's the important aspects here, is to understand concepts, and equally important to be able to apply these concepts to solving different problems. So once again, just a reminder, we're here as scientists not just to learn the facts or the content here of organic chemistry, but using the information here to train our minds to become better thinkers and better problem solvers. So keep working hard, and I'll post more information on D2L shortly. Okay?